Good morning. In today's lecture, we will continue with the topic about position sensors, and we will finish the talk with a special group of sensors that are called proximity sensors. All sensors that we've seen so far were continuous sensors. So the continuous sensor gave us a continuous information about the distance between the sensor and the object. So the output signal was either some voltage, could be some current, or it could be some number. In any case, it was some distance. Continuous sensors are useful in many applications where you really need to know what is the actual distance. But there are many applications where you just need to know if the object is present or not. And you don't care about the distance, you just need to know if the sensor sees the object or if it's not visible. Some examples. Let's imagine that you have a packaging line, and that on this packaging line you are packing some products into boxes, and then it's important to know if my product is there, if my box is there, but I don't really care if the box is 1 centimeter away from the sensor, or if it's 1.5, or if it's 2 centimeters. So in this case, I don't need to use a proximity sensor, the continuous sensor, but I can use a different group of sensor which is called a proximity sensor. And the advantage of the proximity sensor is the price, because proximity sensors are usually a lot cheaper than continuous sensors. So you reduce the price of your application, and you can still use it in packaging lines and production lines, because in those applications you really don't need to know the distance between the object. The output of the proximity sensor is a logic signal. So it's not some voltage that is proportional to the distance, but the logic signal means that it is a 1 or 0. We can also call it high or low. So in this case, it's just a signal that is saying yes or no, the object is present or the object is not present. I will show you 3 examples of proximity sensors. One will be based on inductivity, one will be based on capacity changes, and one will be based on optical properties. We will see that some of them can be used in all applications, and some of them can be used only for a specific group of objects. So we'll need to limit it based on the material from the object that we're detecting, or based on the color, based on the transparency, and so on. So let's take a look first on the inductive sensor. The inductive sensor works on the changes of inductivity. So the main component of the inductive sensor is an inductor. Here we see that we have an inductor, and this inductor is powered with AC current. So we are creating an AC current in the inductor, and this will create an AC magnetic field around the inductor. So here around this inductor there will be a magnetic field. You can imagine that the magnetic field can look like this. So this is one half of the field, and this is the second half. So this is how the magnetic field typically looks like. And we can see that when the object will enter the magnetic field, it will change the properties of the field. So if this object is ferromagnetic, it will alter the magnetic field in such a way that it will look something like this, and the magnetic field therefore will be distorted. So we are looking for the changes of the magnetic field around the inductor. Typically it's done with the help of an oscillator. So this oscillator is the circuit that creates the AC current in the inductor, and when we approach the object, these properties of the inductor will change, and we will have different frequency and different amplitude of the oscillations. So the output from the oscillator will then be processed with a detector circuit that can detect the changes of oscillations, and the output of this detector circuit will be a flip-flop circuit which will produce a 1 or 0. So here on the output we will have either 0 or 1 based on the object, if it's there or if it's not there. For an inductive sensor, it is very important that the object itself is ferromagnetic, or at least it needs to be conductive electrically. So inductive sensors work only with conductive objects, so typically metals, and they work the best with ferromagnetic materials. So they do not work with materials that are not conductive, such as plastic, glass, wood. So the object needs to be conductive, and best is if it's ferromagnetic, so if it's from iron. So inductive proximity sensors are traditionally used to detect metallic objects. Here is an example how the sensor looks like. For some reason there is no table here in my picture, so I have to do it without it. There is supposed to be some table. Let's take a look first on this picture here on the left. Here we see the detection zone of a proximity inductive sensor. So here is the object that we are detecting. Here it's called the plate, because it's typically a plate of metal, a box or a teeth that you use for detection. Here is the shape of the detection zone. So this is how it looks like. This is the shape of the magnetic field where we detect the presence of the object. And we can see that there is a certain distance. Typically in datasheet it's called operating distance, and here it's called SN. That's the typical name as you see here in the datasheet. And the distance is defined between the sensor and between the object in this direction, in this vertical direction. So if we approach the object from the side into the detection zone, that's what we see here on the figure on the right hand side, then here we have this detection distance over there, but here this detection distance, since we're approaching from the side, will be this one. So the detection distance in the datasheet applies only if we are approaching from the front of the sensor, and if we are approaching from the side of the sensor, we have a smaller detection distance. The detection distance is a function of the sensor diameter. So here we have the diameter of the proximity sensor. It's typically normalized to some metric size screw. So it could be M12, it could be M8, something like this. It could be even larger or smaller. And the dependence of the sensing distance is the following. If this diameter is larger, then the sensing distance gets larger as well. In any case, it is quite small. It is a few millimeters. So for example, here in this data sheet that you see on bottom right, you can see that the distance for this particular sensor is 1 millimeter, and the external diameter is 3 millimeters. So this was a sensor that had an external diameter of 3 millimeters. If, for example, the external diameter would be something like maybe 12 millimeters, then the operating distance that you can expect would be few millimeters. let's say between 5 and 10 millimeters. So it's definitely nothing like 1 meter, but it's few millimeters. The detection distance also depends on the materials. So this operating distance that you see in the data sheet, this only applies for ferromagnetic materials, so for iron. If it is steel, then it depends actually on the properties of the steel, but it's a little bit smaller. So for steel, we can say that's about 0.9 of this detection distance. So in a disk sensor, it would be about 0.9 millimeters. For other metallic materials that are not ferromagnetic, such as copper, aluminium, brass, bronze, the detection distance gets significantly smaller, and it could go to around 0.4 to 0.3 of the detection distance. So if I have a sensor that has an operating distance of 1 millimeter for iron, then approximately for aluminium it will be something like 0.4. And if my object is outside of this detection distance, it will not get detected. So for proximity sensors, it is quite important to select the correct operating region, so operating distance, as for your application, so that it works correctly. And then it's quite important to maintain the correct distance with some mechanical setups. We'll see a few examples in a second. The output of the sensor, that is proximity, is 0 or 1, so yes or no. Typically, the way it is named is called PNP and NPN. We'll see again in a second what this means. And then you can find something like this, NO or NC. NO stands for normally open, and NC stands for normally closed. So if it's normally open, it means that you have no signal on the output when the sensor does not detect the object, and when you approach the object into the detection distance, it will close the output switch and it will give you some signal. On the other hand, if it's NC, normally closed, it means that you have a closed switch at the output at all times unless the object is detected. So the switch at the output is on, and when you approach the object, then it gets off. Whatever you choose, it really depends on your application. Because for some applications you need to have this normally open behavior. For some other applications, it's more advantageous to have the normally closed behavior. Let's take a look on some examples of proximity sensors. Here on bottom left, we can see what's actually inside of this inductive sensor. So the construction is relatively simple. We see that inside there is an inductor. This inductor is placed on a core. The core is here and there. So the resulting magnetic field will look like this. Here it will go like that, and it will go in the core, and here it will close in the core and will do this. The field is symmetric, so it will be all around the circumference, and here at the other area, the other half of it will do something like this, and it will be close through the core, and then it will be going like this. So this inductor is creating the magnetic field, and this core is guiding the magnetic field where we actually want it. So here the magnetic flux goes in the core, but here it has to go through the air, and it's protruding into the free space, and when we approach the object, it will distort the magnetic field, change the properties on the inductor, and we will be able to detect this. The inductive sensor from the outside typically looks like a screw. So here you can see a screw like this. This would be probably M12 or M20, something like this, with a large diameter. And it can be from metals or it can be from plastic. In any case, the cap that we see here on top has to be from some material that is not ferromagnetic, because if it would be ferromagnetic or conductive, we would guide away the magnetic field and it will not stick out from the sensor. So you can see that even here in this metallic encasing version, here this is a plastic cap, and the reason is that we do not want to shield away the magnetic field. The screw here, the thread on the external surface of the proximity sensor, that is used to mount the sensor and also to adjust correctly the distance. Then simply by moving the thread, the sensor in some hole, and by adjusting those knots, you can precisely adjust the distance between the proximity sensor and between the object itself. As I said, there are many diameters that you can actually find. So something like this, a small diameter, could be something like M8, could be M3, so whatever size you require. It could be also something very large, so typically this is M36. So here this diameter is 36 millimeters. In this case, we can see that it is all made from plastic, and here we again have the thread so that we can adjust the distance. As I said, there is an inductor inside. So the inductor is somewhere here in this region, something like this. And there is also an electronic circuit. So the electronic circuit is at this region. And the electronic circuit is the oscillator, it's the detector circuit, and it's the flip-flop circuit. And it also takes care about the power supply. The typical range of power supplies in industrial systems is somewhere between 9 to 36 volts. So typically you find the voltage directly written on the sensor. You can see it, for example, here. In this sensor they say it's between 10 to 45 volts, maybe even larger. So it can operate with the industrial voltages. Typically the industrial systems are powered with 24 volts. So it can be 24 volts, it can be 36, something in this area. The last example shown here on top right is an example of inductive sensor, but it just has a different shape. So again, here there is an inductor. This is the sensitive area. This is where we approach the object. It has a different shape. Here we see the mounting holes, so there is one mounting hole here, and there will be one mounting hole over there. By using those mounting holes, we mount the sensor on a frame, and we will adjust the distance between the object and between the sensor itself. Now typically all proximity sensors have an LED on them, so that we can see directly on the sensor if we see the object or not. So this is the example here. This is the LED that will either be on or off if we see the object. It's also the case of those sensors that you see on the left, but in this case the LED would be from the back side, so it will be somewhere around here or somewhere around there. So we don't see this on the picture, but there is probably not a sensor that does not have some LED, and the reason is that it's very simple then to see if the object is really detected or if it's not detected at all. Let's take a look on some applications where you can actually find the proximity sensors. You can see this picture on the left hand side. This is an ABS wheel speed sensor. So it's an automotive application. ABS is taking care of blocking of the wheels during braking, and in order to make the ABS system functional, you need sensors on every wheel. So on every wheel we measure if the wheel is actually turning and with what speed, and we can see if the wheel is blocked or if it's not blocked. So typically on a wheel there is this object, this gear wheel, and we can see that those teeth and those gaps, they will create us the object that we are actually detecting. So a proximity sensor can be used as a position sensor, but in this case it can be also used as a speed sensor. If the sensor sees the teeth, we can say, okay, there is the object. If the sensor sees the gap, then we see some other signal. And by counting the teeth and by counting how many teeth we see per some unit of time, we can actually find out what is the speed of the wheel. So this requires that the distance between the sensor and this gear is set to a proper distance. So it could be something like 1, maybe 2 millimeters. If it's far away, then the teeth will not get detected anymore. So you need to adjust this distance to the proper distance. The output of the sensor, as I said, can have two options. It can be the PNP output or NPN output, and the output configuration actually depends what's inside of the sensor. Typically there is a transistor that is used as a switch. So if it is a PNP transistor, here we have the PNP transistor, that's the element, and the load is our output of the sensor is connected in this case between the minus and the output signal. So here we have the permanent connection on the minus wire. The plus wire acts as a power supply for the sensor, and then if this will switch, then it will turn on the current that will then flow through this transistor into our load. And our load can be anything. It can be a voltmeter, it can be an input to the control system, it can be a light, it can be an LED, anything that will tell us that the object is there. So this is called the PNP output or PNP transistor. If on the other hand we have an NPN transistor, we can see that the load is always connected with one terminal to the plus side of the power supply, and then the transistor is switching this to the negative side. So if the object gets detected, this transistor opens, it will act like a switch, and current will start to flow from this load to the transistor and back to the power supply. And again, the load can be anything. It could be a bulb, it could be an input to the computer system, it could be a voltmeter or amperemeter, for example. So those are the types of the two outputs, and the actual output that you choose for your application depends on the application requirements. In some applications you can choose the PNP transistor because here the advantage is that the load is not connected to the positive side, to the positive voltage, and it's connected to the positive voltage only if you have an output signal from the sensor. So in terms of safety, This is the safest connection, because here we don't have any voltage at all, and we turn it on only when we have some signal. On the other hand, the NPN is a little bit less safe, because here we have the plus voltage connected at all times, and if there is some short connection, for example here at those two wires, we will have some current that is flowing through the load. So in industrial applications, a little bit more common is the PNP output, because of this safety feature. On the picture on the right here, we can see the shape of the magnetic field that we actually have around the sensor. So we can see again the coil. This is the inductor that's inside. The part here in black, that's the ferromagnetic core, which can be made from iron, or it can be powder iron, for example. And we can see that by changing the number of turns and positioning of the turns in this inductor, the manufacturer can actually change the shape of the magnetic field. So it's possible to change the detection distance as well. So you can have different detection distance and different shape of the detection zone, even for the sensor that has the same diameter here externally, that this screw diameter is the same. So this allows us to adjust the selected sensor specifically for our application. Let's take a look on the second group of sensor, which will be based on capacity. As the name implies, we will be looking for changes of capacity of a capacitor. So our detection element is a capacitor, which is here, and the capacitor will again be powered by AC current. So this is then the role of this oscillator. So again, it will create an AC current that is fed into the capacitor. The capacitor will create an electric field, and if we arrange the electrodes properly, the electric field will protrude like this outside of the capacitor. So typically it's not like this, that you can see the vertical electrodes, but it can be something like this, that you have one electrode like that and another electrode like this, and then the electric field looks like this. When we then approach the object into the detection distance, if this will be my object like that, then I will again distort the electric field in the capacitor, and I will change the properties of this capacitor. So this capacity will basically have a different value. This change will get detected by the detector circuit, and the output is then connected to a flip-flop, and again on the output we'll have either 0 or 1 if the object is there or if the object is not there. In order to distort this electric field around the object, I need to approach the sensor, and in this case I don't need that the object is ferromagnetic, because I'm changing the electric field and not the magnetic field. So capacitive sensors, they work for all materials, but the material needs to have a different permittivity than the ambient environment. So if this is air, it has a relative permittivity of approximately 1, and here this relative permittivity has to be significantly larger than epsilon r of the air. So if my object that I'm detecting has similar permittivity to air, then it will not be detected by a capacitive sensor. An example, some plastic materials, for example polyethylene pellets, they have a permittivity very similar to air. So it's close to 1. It's not exactly 1, but it's quite close. And therefore those materials cannot be detected. So traditionally, capacitive sensors in the industry are used to detect non-metallic materials. So for example, they can detect plastic, they can detect glass, they can detect paper and so on. But capacitive sensors, they can detect also metallic objects. So they work with iron, they work with copper, they work with brass, aluminum and so on. Let's take a look again on the detection distance. The detection distance is very similar to the inductive sensor. So again, it has some detection distance. Typically, the detection distance is a little bit larger than for inductive sensors, but anyway, it's a few millimeters. Let's say 10 millimeters, 15 millimeters. It's definitely nothing like 1 meter. The detection zone again has this similar shape. So the detection distance is defined if you approach the sensor from the front side, like that. And if you approach the sensor from the side, then this detection distance will get smaller. So again, it's a relatively small distance. The distance depends also on the material, and this sensor detects the best conductive materials. So if we have iron, if we have aluminum, if we have copper, then this gets detected the best. And for other materials that are less conductive, the detection distance gets smaller. So for example, if I want to detect wood or plastic or water, then it will be approximately 0.5 of the detection distance. I'm saying approximately because it actually really depends on the properties of the material. I was saying plastics, but there are many kinds of plastics. So some materials can be detected, some materials cannot be detected, especially if the permittivity is very close to the permittivity of air. That's what was supposed to be here in the table on the left. On the picture on bottom right, we can see the options with respect to the power supply. So on the two pictures on top, we can see that here we have a DC power supply. The output now has two possibilities. Again, it's NPN or PNP. And in this picture, you can see a sensor that has both normally open and normally closed outputs. It's also possible to find those sensors and you can use them in your application. And you can see how it's connected. Here, this is the normally open contact. So unless the object gets detected, this contact remains open. And on the other hand, this is a normally closed contact. So unless the object gets detected, this remains closed. And again, this box, it can represent the load, which can be our input to the control system. It could be some light, it could be some panel meter where we see what actually is happening. NPN, you can see that now it's connected to the plus side. So plus side is always connected, and the NPN transistor switches this wire against the minus wire. Similar functionality, but here we have a PNP configuration, and here we see the signal. This is my output, and here it's permanently connected to minus, and here we see the normally closed output, and here we see that it's all again connected to the minus wire that we can see over there. In some cases, it's also possible to power the sensors directly from the power network, so you don't need an external power supply. And then it works like this. Here we see this is directly connected to the power network, to the phase wire. This is the neutral wire. So this provides the power supply. And here we see the output of the sensor is switching my output signal here against the neutral wire. So the neutral wire goes to the load, but it has to go also to the sensor itself. Again, normally open contact, so if the object is detected, then I see some voltage. In this case, it will be directly the power voltage, the power line voltage. And if it's normally closed, then the voltage here is available at all times. And when the object gets detected, then this switch will disconnect, will do this, and I will have no voltage on the output. So based on your requirements for the application, you can either have this configuration with AC voltage or with the DC voltage. In terms of safety, it is better to have the DC voltage 24 volts, for example, because if then someone will touch for some reason your outputs or your power supply voltage, then this low voltage DC is not dangerous at all. If you use this this AC voltage, it's definitely more dangerous. But on the other hand, here with the AC version, you actually save for the power supply, so you don't have such a complicated connection because you are powering the sensors directly from the power network. Here is an example how we can use the proximity sensor as a position or as a speed sensor. It's a similar application as we've seen the ABS sensor, but in this case we want to detect the speed of the wheel that has teeth, but this wheel is from plastic, so it's from PVC. We can actually see two sensors. Here this sensor can actually detect the teeth from the top side, and this sensor can actually detect the teeth from the side. So both configurations are possible. In both cases, we need to make sure that this detection distance, you can see here this detection distance, is below the detection distance of the sensor. So typically we set it to somewhere as 1/2. This object that you can see here, this box, can be a teeth, or if this would be, for example, a packaging line, then this would be my product and this would be the conveyor belt. So as the object is moving, it's moving like this, and at some instant I see the object like this in the detection area. So I see that the object is there. I have some output signal, let's say 1, and if the object will move, I will be somewhere around here. I don't see the object because I see the gap between this object and this object, and I will have a different signal. The output signal is a logic signal, so it has a 0 voltage or some voltage when the object gets detected or not. So typically what you see on the output is a signal that looks like that. So here we have voltage and here we have time as the objects are moving on the conveyor belt, or if this this wheel is turning. So here is when the object is detected. So let's say this is 1, this is 0. Here for 0 I don't see the object, so here I'm in the gap, and here I see the object, so I'm here at this position and I see the object under the sensor. By counting the pulses, we can count the number of objects. So here I would see 1, 2, 3 pulses like this, 3 ones like that, and this allows me to count it. But if I time it as well, I can also find out what is the speed of the moving object. So you can see here that I am able to measure time t1, and time t1 corresponds to the time when the object is visible for the sensor. If then I time t2 as well, I can time the gap between the objects like this, and by measuring the frequency, I can actually calculate also what is the speed. So if this is a conveyor belt, or if this is a wheel with teeth, I can calculate what is the speed as well. So proximity sensors are useful not only as position sensors or end switches, but they are useful also for speed sensing. We'll see that later today at the end of the lecture. Here are a few examples how the capacitive sensor looks like. From the outside, you can typically not tell if it is an inductive sensor or if it is a capacitive sensor. They look very similar. You can find it out by using a piece of iron, because if you approach the sensor from this side like this, then inside of the inductive sensor we know that there is a ferromagnetic core. So this core is typically magnetized, and it will attract very slightly the piece of metal. So if you take, for example, a screwdriver, approach the sensor, and if it will be attracted, then it will be an inductive sensor. On the other hand, if you approach it and nothing happens, then it is most likely a capacitive sensor. From the outside, it looks very similar. Again, it has typically the shape of a screw like this with a thread, and this thread allows you to adjust the distance between the object and between the sensor by using those two nuts. Another way how you can actually test if it's a capacitive or an inductive sensor is to turn it on and approach different materials. We know that inductive sensors detect only conductive materials. So if you approach copper or piece of iron, a screwdriver for example, then it will be detected by the inductive sensor. Capacitive sensors detect the conductive materials as well, so you will see it as well. But if you approach a non-conductive material such as a piece of plastic or wood, then it will be detected only by the capacitive sensor. And if it's an inductive sensor, you will not see any reaction at all. Again, the capacitive sensors, they typically have an LED. So somewhere here there is typically an LED, or somewhere there where we can actually see some light if the sensor sees the object or if it does not see the object. Now some sensors are NPN, some sensors are PNP. We can see the connection here. So here we can see that this is the brown wire, this is the plus voltage, this will be my output signal, and here we'll have the minus voltage. And again, it will be in most cases powered with a voltage between 9 and 36 volts, which is the standard industrial range for power supply voltage. We can see that this is the NPN output, because here we have a permanent connection to the plus voltage. On the other hand, here the V plus voltage is connected there, and here the minus is connected permanently. So this sensor is a PNP output signal. In both cases, it can be normally open or it can be normally closed. There are many versions. Some have a metallic casing like this, some have plastic casing like that, but the functionality is exactly the same. On the right hand side, the bottom corner, you can see one example application. But this is a packaging line, and let's say we want to pack the products, we want to count the products that are running on the conveyor belt so that we can pack them properly in a box. So here you can see the sensor. In this case it is a capacitive sensor. This could be a plastic box, paper box here, plastic bottle, and we need to detect it with a capacitive sensor. We can count how many objects we have, and then we can use this number to actually pack them properly in a box, I don't know, 6-pack for example. So capacitive proximity sensors are typically used for those applications. Packaging lines, production lines, counting of some objects, measuring speed of some objects that are non-metallic. They can detect metallic objects, but in industrial systems, traditionally, metallic objects are detected by inductive sensors, and non-metallic objects are detected by capacitive sensors. So that's the second group of proximity sensors. And the third group, and the last one that I will show you, is the optical sensor. And we'll see that optical sensor can detect different materials than the inductive or capacitive sensor, but it will have, for example, trouble with transparent objects. So let's see how it works. We need a source of light. I will say light, but typically we do not use visible light, but we use infrared radiation. So it's based on near infrared, somewhere like 880 nanometers, 950 nanometers. So we cannot see it with our own eyes, but for example, with if you look with some cell phone on it, you will be able to see the infrared radiation. So it's the same wavelength as you know from infrared remote control for TV, for example. So this source is an LED that operates in the near infrared range. Then we need an optical system, also a lens and a filter, and we project the beam of light on our object. This object will reflect the beam of light back to the sensor, again through a lens and to a detector. The detector can be a photodiode, it can be a phototransistor, it could even be a photoresistor. This actually depends on the speed that we require from the sensor, but typically it's a phototransistor. And if we have a reflection, then this means that the object is there. So the major difference between the optical sensor and the capacitive and inductive sensors will be in the detection distance. Based on the optical system, the optical sensor can work up to few meters. So it will have a very large detection distance. On the other hand, it will not work properly with transparent materials. Now what you see here is a sensor that is based on reflection from the object. So if the reflection from the object will be different, I may not be able to detect the object. So optical sensors are typically specified for a given color of the object. So let's say it's typically a gray color with a certain color coordinate in the color coordinate system. So it's typically specified with a gray object with certain properties. Now if the object is not there, I don't see the reflection, and the output of the sensor is some signal. Now it's a proximity sensor, so the output is 1 or 0 if I see the object or if I don't see the object. So it's again not a continuous signal. The output again can be an NPN or it can be a PNP, and it can be normally open, it can be normally closed. It's exactly the same like for the other proximity sensors. The second option that we have in optical sensor is to detect if the object is interrupting the beam or if it's not interrupting the beam. So here on the left you can see the same principle. We can see the reflection from the object. So the LED produces the light and the detector will detect the reflection. We have a second option, and here we see that we have an LED. This produces a beam of light, and this is my detector. The optical system is not shown, but you need it anyway, because if you do it just like this, then the angle where this radiates will be very large. It could be something like 90 degrees, so you would have some radiation field like this, and it's not a beam like that. So in order to have a beam like this, you would need a laser diode. When the object will interrupt the beam, the detector will not see it, and here I will have a signal. So let's say that this will give me 0 and this will give me 1. So object is detected and I see the 1 on the output. Here is such an example how the sensor looks like. So this sensor actually works with the reflection. We can see that it has two optical systems. Here there's one lens over there and one lens over there. So one of them is the transmitter and one of them is the detector. So it will produce a beam that's going like this, gets reflected from the object, and then it bounces back and I can detect it. The sensor like this can have a detection distance of let's say few meters, but it can start also from small distances. For this particular sensor we can see that they say SN, the detection distance, is 17 millimeters. So the distance between the sensor and this object will be 17 millimeters. If you want to detect larger distances, if you want to detect larger objects, you need to go to this second principle where we interrupt the beam. And here it's actually limited just by the optical power of the beam. So if this is a laser beam, for example, it can be easily few meters or even more. And you can see such an example here of such an application. So we want to detect the size of the tile that is running on a conveyor belt. Here we have one sensor on one side of the conveyor belt and a second sensor on the other side, and one will be the transmitter and one will be the receiver. It looks like that this is on the right hand side, this is the receiver, because here they have the warning here, so it's probably, it looks like it's a laser beam, and this part will be the detector, and this is the laser beam that we are actually detecting. So we can detect if the object is there, if we know the speed with which it is moving. We can also measure the distance. It will not be very accurate, within maybe a few millimeters accuracy, but we can distinguish if I see the tile or if I don't see the tile. So again, this is used in production lines, in packaging lines. You count the objects and then you know, okay, now I have counted 20 tiles and I can close the box and I can move to another box and start packaging a new one. Optical sensors, obviously, they require that there is a reflection of the beam. So if it's an object like this, I need some reflection. If it's an object like this, I need that the object will block the beam and there will not be any radiation going to the detector. So optical sensors are not a good idea for transparent objects. So if you have a glass tube or a plexiglass tube or a plexiglass sheet, then it will most likely not be detected properly with the optical sensor. I'm saying most likely because if an object is transparent for us in the visible band, it does not mean that it's transparent also in the IR band. So it can be different. So some plastic materials, for example, are transparent for visible light, but they are not transparent for IR light, so they can be detected with optical sensors. But you need to try it out to see if it actually works for your application. Okay, so that's all for position sensors. And now we still have about 30 minutes left. So I will start a new chapter and we'll be talking about speed sensors. We will not be talking today about acceleration sensors. I just left the name on the slide, but we will be talking about it next week. Now you will see that the speed sensors will be in some cases very similar to the proximity sensors. In fact, it's the same group of sensors. So we will see that, for example, this sensor, this inductive sensor, will be working in exactly the same way like you've just seen the proximity inductive sensor. The other sensors will be a little bit different, but we can use in most cases a proximity sensor also as a speed sensor. Now I will not be talking about the mechanical sensor at all. This could be, for example, a mechanical speed sensor, but we will be talking only about sensors where you actually have some electric output signal. So we can connect it somewhere. We can connect it to a display, we can connect it to a computer system, and we can do something with the signal. So I will start with the electromagnetic speed sensor. This sensor is also called a DC tachogenerator. So this is an electric machine, and the output of this DC tachogenerator will be a signal that is proportional to speed. So I cannot detect position with this, but I can detect the RPM. Here we have a shaft, and this shaft is connected with a coupling to my machine. So I want to measure the speed of a motor. I want to measure the speed of a wheel or of some axis. So here there will be my source, and here there will be a coupling, and here we'll have the shaft. This is an electric machine, and it has a stator and a rotor. Now the stator is composed of few components, and one of the most important ones is the ferromagnetic stator, here the ferromagnetic ring. So this is a cylinder that goes around the circumference like this, and here we have some poles. In my picture I am showing just 2 poles, but it may have a different number of poles. They can be 4 or 6 or even higher number. The construction is almost the same like for a normal DC motor. So if you had some classes about electric machines, then here you should be able to recognize a DC motor. In order to make it work, we need to create a magnetic field. Now in the case of DC tachogenerator, this magnetic field is created with a permanent magnet. So here we can see the North Pole and the South Pole. So this is a cylindrical permanent magnet, which looks like this. This is a cylinder. And it's polarized in such a way that one half of it, let's say here the part on top, is the North Pole, and on the part on the bottom is the South Pole. Why do we need a ferromagnetic material? Well, because we need to guide the magnetic flux in the magnetic circuit. So here, these red curves, they show us what is the magnetic flux looking like. So here the magnetic flux is created in the permanent magnet. It's going through the air gap, through the pole, through the ferromagnetic ring, and back into the permanent magnet. So it's closed like this, and it's closed like that. In order to make it work, we need the ferromagnetic material also on the rotor side. So typically here this is a cylinder of iron, and on this cylinder we have the permanent magnet. It's either in sections or it's really just like a cylinder. This whole assembly is then attached to the shaft. Typically it's a press fit. Here between the rotor and the stator, so this is the stator, and this is stationary as well. But here we have the air gap, and in the air gap we have an inductor, a winding. Here I am showing it in green. So here this is my winding and this is my winding, and this winding goes around all the air gap, and it can rotate in the air gap. So when my machine is turning, then this winding is moving in the magnetic field. And now it's nothing else than an inductor that is placed in a variable magnetic field. So what will happen in the winding is that we see some induced voltage. So in those winding here in the air gap, we will have some induced voltage. And in order to connect it from the rotor to the stator, we need a device that will be called a commutator, and here a brush. So every section of the winding is connected to the section of the commutator, and then it has a second pole on the other side. So this would be one inductor like that, and the second wire from the inductor will be here and will go to the section of the commutator. And the reason for the commutator is to rectify the voltage. Now if we would have only single winding on the rotor, then the output would be AC voltage, and we could measure the frequency, and we could actually use this as a speed sensor as well. But in the case of a DC tachogenerator, our output signal will be a DC voltage, and the amplitude of this DC voltage will be a function of speed. So I need to rectify the voltage that is produced in the winding, and this is the task for the commutator. So the commutator acts like a switch, and it's switching between different sections of the winding so that we have the DC voltage on the output. So the commutator is rotating, and then the voltage is being collected by a brush from the stator. Now for DC motors or DC generators, normal electric machines, the brush is typically made from carbon. So it says this is a stick of carbon, and it's used as a brush. For DC tachogenerators, we want to avoid the high loss on the brush, and therefore the brush is made from silver wires, because this has a lot smaller voltage drop on the brush. So there is almost no voltage drop between the commutator and the brush. If this would be from carbon, then the voltage drop is typically something like 0.5 volts for one brush. So let's take a look on how the rotor looks like. Now what you see on this picture, this is actually not a DC tachogenerator, but this is a DC motor, but it has a same construction. What we see here, this is the commutator. Here we can see those are the individual sections on the commutator, like that. They are electrically insulated, and this and this are the wires that are connecting the windings that we find on the rotor. Now we can see that this piece of material, this is iron. It's typically laminated electrical steel, and the wires, they run in those slots like this. So for example, this looks like it's going in this slot, and then it will go to the other side back, and on the other side it will go to a section that will be approximately somewhere here. So 180 degrees shifted, and we will connect the brush with one section like this here. There will be one brush, and then there will be other brush going like that. And as the machine is turning, it is switching the brush between this section, this section, this section, and this section, and so on. And the resulting voltage that we get is a function of the angular speed. So we can say that the voltage that we have on the output of this machine is a function of angular speed. That's what I want, because I want to use it as a speed sensor. It is a function also of the magnetic flux phi, but since we have a permanent magnet, then this magnetic flux is a constant value. And then it's a function of how is the machine made. So it's a function of construction. And this is then hidden in this constant. It's a constant value. We're not changing the construction during operation. So we can see that this will get us a linear dependence. The input will be angular speed, and the output will be voltage. And the constant of proportionality will be the construction and the magnetic flux. Now the output voltage is what I want to measure, but the DC tachogenerator is acting like a voltage source. And if you load a voltage source, then you take some current, and the voltage on the output will actually drop. So the ideal load that you should connect to such type of voltage source is going to infinity, so as high as possible. Otherwise, you will have a voltage drop, and you will measure a smaller voltage. Now let's take a look on how we can actually see the voltage on the output. So I was saying that the commutator acts like a mechanical rectifier. So the voltage that we are actually creating in the rotor is an AC voltage, and we are rectifying this voltage. So the commutator acts like a switch, and it switches the sections on the commutator. So what we have on the inductor is actually a sinusoidal voltage. You can see here the part of it. So this, for example, shown in red, this will be a voltage that we see from one coil on the rotor. Then we have a coil that's next to it, the one shown here in yellow, that's the second section. In green, third section. In blue, fourth section, and so on. And if we actually rectify this voltage, what we will get is just those peaks. So we want to get this voltage because we want to cut away everything else except the peaks. Now in the ideal case, the commutator would have an infinite number of sections. So this would be a flat line. It would be something like this, an ideal voltage. We are limited in the number of sections that we are actually able to make mechanically on the commutator. So this will limit us the rectification quality. Therefore, on the output of the DC tachogenerator, you will always find this delta V component, and this delta V component will be a function of the number of sections. If it has more sections, then it will be smaller. If it has less sections, it will be larger. And we can say that this is the error of speed measurement that we can actually make. Now typically the steady state characteristic looks like this. Here we see the speed. This is my angular speed omega, or it could be RPM, doesn't matter. And the output voltage is dependent on the speed. Now we've seen the equation. This is a linear equation. It starts from 0, and then we have a linear response. Unfortunately, we need to look also for the output resistance, of the load resistance that we connect actually to the output. Now, if it's an unloaded sensor, if the load resistor RL is very high, then we see a linear dependence like this with a larger slope. Now if we load it more, then the slope will actually decrease. So if you use a DC tachogenerator, you need to take care about the load resistance that you are actually connecting to it. So in manufacturer specifications, you will find typically some number saying that do not connect the load resistance outside of this range, for example. Now let's take a look how this looks like. I will start with the picture on the right. Here we can see that this is it's a relatively large sensor. Now in this case it has a flange to mount it to your application, so you use those holes on the flange to mount it somewhere. And here we can see that here we will attach the coupling, and here we will attach it directly to our machine. So it could be a speed sensor for an electric motor, for an elevator, for a conveyor belt, for an axis of some machine. Now this requires a coupling to connect it. Now here on the left you can see a little bit different version, and we can see that there is no axis in this case, but in this case we have to push directly the rotor onto the shaft of our machine. So that's the whole. Here you need to have the machine ready for that. You install the rotor in there, you push it on the shaft, and then you assemble the stator like this. In both cases it will have an output voltage that is proportional to speed. Now let's take a look on some key specifications so that we have an idea what we can actually expect from the DC tachogenerator. So here is just an example of some manufacturer. We can see approximately the speed range, so it's a few thousand RPM typically. It's nothing larger, because for larger speeds we prefer non-contact speed sensors. So you can see few thousand RPM is the maximum speed. Now we know that the dependence between speed and voltage is linear, so we need to know only the slope. So it's specified typically like this: rated output voltage at some speed. So if for this sensor I have 1000 RPM, I will have 50 volts output voltage. Remember, this is a DC voltage. In some cases it can be larger voltage, something like, well, in this case it's virtually the same, because here they specify at 4000 RPM is 200, which is nothing else than 50 volts for 1000 RPM. But you can find the DC tachogenerators that have 2 volts for 1000 RPM, the smaller ones, or you can find DC tachogenerators that have 80 volts for 1000 RPM. This maximum output current, this is what I was talking about with respect to the load resistance. So if I choose the load resistance to be too small, then I will take a large current, and I cannot take a larger current larger than this value. So for this model it's just 10 milliamperes. For this model it's 70 milliamperes. So this is telling me that the DC tachogenerator cannot provide me a lot of electrical energy. It's not a generator used as a power supply, but it is a sensor. Here we can see the moment of inertia. So this I need to add to the moment of inertia to my electric machine if I want to do mechanical calculations, for example. We can see also here, for example, the permanent magnet type, so alnico, it's aluminium, nickel, cobalt magnet. We can see ferrite magnets, rare earth, that could be neodymium, iron, boron permanent magnets. And we can see also the weight. So typically the DC tachogenerators are quite bulky. They weigh something, and you need to take this into account when you're designing the machine. With a DC tachogenerator, remember that here we had this ripple, and this ripple is limiting us what is the accuracy. And typically with a DC tachogenerator you cannot measure with a better accuracy than about 1%. So if you want to have a more accurate reading, then you need to use a different kind of sensor. We'll be talking about the other sensors next time. Now we will do the Moodle test, and you have a chance to get some points from it.